Hi! Today we're going to learn about the ratio test in calculus. Let's say we have a problem like this. Is the series from n equals 1 to infinity of n squared over 2 to the n power convergent or divergent? Well, how do we know whether this is convergent or divergent? Well, here we can see that we have a fraction, and the numerator and the denominator are growing and have different type of rate growths. So this one is 2 to the nth power, and this one is n squared. So you can see that they grow very differently. So how do you figure out whether this is convergent or divergent? So this is where we use the ratio test. So the ratio test is good when there are two different types of rate growth in the numerator and the denominator. The ratio test says that if we have the sum from n equals 1 to infinity of a sub n, then if the limit as n approaches infinity of the absolute value of a sub n plus 1, or this is a sub k, sorry, and this is a sub k plus 1 over a sub k. So if this limit is equal to L, then if L is greater than 1, it's divergent. If L is less than 1, it's convergent. And if L is equal to 1, then the test is inconclusive. And you have to use a different test. And notice that inconclusive does not mean the same thing as divergent. Inconclusive means that you cannot use this test. And the test is basically invalid. So let's apply this to this problem. So if this is our sum, this whole thing, that means that we have to find the limit of the absolute value of this, which would be a sub k, as n approaches infinity. So this would be a sub k. So that means that we have to find the limit as n approaches infinity of the absolute value of n plus 1 squared over 2 to the n plus 1 power, all over a sub k, which is n squared over 2 to the n power. But we know that when we're dividing a fraction, it's the same thing as multiplying the reciprocal. So we just multiply the reciprocal of a sub k, which is 2 to the n power, over n squared. And this absolute value sign closes it. So we get the limit as n approaches infinity of n plus 1, this should be k over here. So we have the limit as n approaches infinity of n plus 1 squared over 2 to the n plus 1 power times 2 to the n plus 1 power over n squared. So we have a sub k plus 1, a sub n plus 1 here now, and it's divided by a sub k, or multiplied by the reciprocal of a sub k, which is 2 to the n power over n squared. So now how do we simplify this down? Well, we know that this would be the limit as n approaches infinity of, so we have n plus 1 squared. Now we could expand that, but let's not do that right now, times 2 all over 2 to the n plus 1 power, multiplied by 2 times 2 to the n plus 1 power, n power, over n squared. So as we can see, we have two exponents with the same base, so we can apply exponential rules. So because we can move our terms around and get 2 to the n power over 2 to the n plus 1 power. So that would be equal to 2 to the n minus n plus 1 in parentheses. So this would be equal to n plus 1 squared over n squared. So we're just moving terms around, times 2 to the n power over 2 to the n plus 1 power. So now we can just subtract this exponent from this one here. So minus n plus 1. We can get rid of this denominator. Minus n plus 1 becomes minus n minus 1. So the n's then cancel out, and we're left with 2 to the negative 1 power, which is equal to 1 over 2, or 1/2. So this is now equal to, so I'm going to rewrite it here, 1/2 times the limit, because 1/2 is positive, we know that it can go outside the absolute value symbols, because it's positive, and because it's a constant, now it can go in front of the limit. So we're just applying limit rules, and the absolute value rules, I guess. The limit as n approaches infinity of n plus 1 squared over n squared. So what do we do here? Well, we could expand this in the numerator and figure out what it is as the limit approaches infinity. But because we know this is a rational function, and we know that as n approaches infinity, the other terms only the dominant terms will matter, we can basically find the dominant term in the numerator and the dominant term in the denominator. So in the denominator, the dominant term is n squared. What about in the numerator? Well, in the numerator, the dominant term would also be n squared, because this expanded would be n squared plus 2n plus 1. The 2n and the 1 are not dominant terms, so those won't matter as we approach infinity. So this becomes, the numerator roughly becomes n squared as n approaches infinity. So we get n squared over n squared. So this is only as n approaches infinity, which is equal to, over n squared. Let's leave it like this because we can't cancel them out because, or in our heads we can't cancel them out because the numerator is actually not n squared. But the limit as n approaches infinity of this would be equal to 1. So this would be equal to 1/2. So now we know that this limit is equal to 1/2. So what does 1/2 mean? Is this convergent, divergent, or inconclusive? Well, here we have 1/2. So we know that because this 1/2 is equal to this limit, the 1/2 is equal to L, because we said that this limit is equal to L. So is L greater than 1? No, 1/2 is less than 1. So L is not greater than 1, that means it's not divergent. L is not equal to 1, that means it's not inconclusive. And because L is less than 1, that means it's convergent. So the answer to this problem is convergent. And I don't know where to write this, so I'm just going to box it. So today we learned about the ratio test in calculus. Thank you for watching this video.